I'm from Sonavation, a company located in South Florida, United States. This talk was originally scheduled to be given by our Chief Technology Officer, Dr. Rainer Smith. He was the primary person to implement and develop the technology and sensor. Unfortunately, he was not able to make it, so I'm honored to be back to my home country, Taiwan, to give this talk for him. So about the 6 billion people around the world relies on the mobile device like the tablet and the mobile phones on their daily lives, like they do the online shopping and the banking and post status on the social media, and even monitoring their personal health using their mobile device. However, there's an increasing threat to everyone due to the unauthorized use and fraud and terror attack. And mobile devices are especially easy to be attacked compared to a general computer like a desktop or laptop, because there are millions of different applications. They may open an outlet to leakage your data and the information to the attackers or hackers. And also mobile devices don't have the computing and battery power to run the antivirus or anti-malware software. Another reason that mobile device is easy to be attacked is because people use bad password. These are the top 25 most common password in 2014, and you can see the number one is 123456. Is even not changed from 2013, and because people are lazy to use more sophisticated passwords, so the hacker don't need to be work hard to break into your device and to steal your information or even money. So based on this result, there are about 2.5% of all the device, means possibly hundreds of millions of the device are protected by this 25 password. So if there's a more secure way to use to set your passwords to secure your devices, yes, people use biometrics. Biometrics can present your personal identity, like the previous speakers talked, and they provide a more secure password and PIN. So biometrics include the iris pattern and face pattern, your voice, your palm print, and the fingerprint. Among all these biometrics, fingerprints is the most easy, most adaptable to most of the user, and the fingerprint sensor is the most convenient. So there are 3 types of different fingerprint sensors currently on market. First one is the optical sensor, and if you at the airport immigration, they take the fingerprint using optical sensor, fingerprint sensors. However, optical sensors usually are too big and sometimes expensive, so it's not possible to integrate an optical sensor into your cell phone device at current stage. And the second one is capacitive fingerprint sensor. Like Apple, they use this type of sensor on their device. They call it Touch ID. And just like the second speaker said, already have, when the iPhone released, there someone already can easily spoof that. So the third one is ultrasound. There are a few of advantages using ultrasound as a fingerprint sensor. The first one is, this is a table compare the 3 types of sensor I just introduced, and the parameter they use to differentiate the fingerprint structure, ridge and valleys. So you can see ultrasound, we use the acoustic impedance different to see the ridges and valleys. So ridge is typically your human tissue, and the valleys are air, so their acoustic impedance can get a contrast about 4,000 to 1. It's much higher than the other 2 modality. And another advantage of ultrasound is it's able to penetrate through the skin, and we can use ultrasound to access the subcutaneous information. And this advantage is not achievable by the other two modalities. So back to spoofing, even using ultrasound, it can still be spoofing, and fingerprint sensor can be easily fooled. And these two imaging in the center is a real fingerprint, and the right one is a fake fingerprint. We left our fingerprint everywhere when we touch something like your coffee cup, your laptop, and your cell phones. And the attacker or hackers can easily take your fingerprint and make it a mold, a fake fingerprint. There are a bunch of different ways to do this. They use different material. They can do the fake fingerprint in a few minutes, even don't need to be hours. So over the last 10 years, Sonavation want to deliver ideal that we want to have more secure signature or a password. We want to combine the fingerprint and also the ultrasound pulse echo subcutaneous imaging. We use these two to combine and get the unspoofable identity. So we have a fingerprint, and we can see subcutaneous biometrics under in your fingertips. It can be bone or vessel distribution. The challenge here is we need to have a high resolution for the fingerprint. It's 500 dpi dot per inch. And we need to use the same sensor to do the subcutaneous imaging. So here is a brief introduction of how we do the fingerprint. And this is a simple model of the acoustic sensor. And we use the method called acoustic impediography. It's major imaging the acoustic load. And we have a sensor here with PZT pillar as embedded in polymer substrate, and we have a DC voltage source to send a voltage signal to vibrate the sensor. And the acoustic load on the top determine how the pillar resonant. So you can imagine that each sensor is vibrate like a bell. And the frequency determined by the resonant frequency and how you drive the sensor. And if the sensor is in contact with air, the belly part, it can resonate freely, and you got a large acoustic amplitude. In the contrast, if the sensor is in contact with ridge, it's like you put a hand on the bell, so it cannot ring that freely compared to the left cast, the left one. So you got a smaller acoustic amplitude, and this is the contrast of how we differentiate a ridge and valley. So we will need an array here, either a 1D array or 2D array, and put underneath your fingertips. So once the element is underneath a valley, it can resonate large, and we got a large acoustic amplitude. And if it's in contact with a ridge, you got a smaller amplitude. And then we can reconstruct the pattern underneath the fingerprint by each according to the response of each sensor. And the resolution is determined by the density of the element, and it's not determined by the acoustic diffraction. So if we want the 500 dpi resolution, the density of the element is 500 sensor per inch. So there's another problem, because if we want the 500 dpi and the 1 inch times 1 inch sensor, totally will be 250,000 sensors. For each one, you need an electrode on the top and bottom to individually address in this element. So they will be very complex, and also you need a very complex control unit to drive in and get the signal from each sensor. So here we use a crosshatch pattern. You can also call it row column addressing. So on the top of the sensor, we connect the row column with one electrode, so they can be active or driving by the transmit signal at once. And in the other direction, the column, we use another electrode on the bottom. So the received signal will be from this electrode is from all the sensors along this electrode. So how do we get the signal from one sensor, not from all the sensor along the line? So we transmit one line and then receive at the other direction, because the transmit line is only activate this element, not all other elements. So the receive line, although the signal is from all the sensor, you got the response from the single element. So we can do a scan through the 2D matrix, and we got the full 2D pattern of the fingerprint. And the signal will be amplified, filter, and analog to digital converter, and some imaging processing to produce the final fingerprint. So here shows some imaging from our sensor. We have two types of sensor. The first one is a swipe sensor. It has a smaller area. This one, I believe, is 256 times 20. And so when you do the fingerprint on the swipe sensor, you need to move your finger swipe. So the get imaging is a partially small imaging, and you need to do stitching to get the final one. And the other one is a 2D array, a large sensor, and this one, you just put your finger on the top of it, and then you can get the whole map. And this one is 384 times 256, and based on 500 dpi resolution, this is about 2 centimeter times 1.2 centimeter. And in both imaging, you can see the ridge and valley flow clearly, and also for the touch sensor, we can also see the pulse along the ridge pattern. We compare the fingerprint from our touch sensor in the center, this imaging, and also from optical sensor. The finger was from the same person, so we find they are matched to each other. So the other question is the cell phone company, they tend to remove the home key, home button, or any button on the top, on the surface of the cell phone. They want, the reason is to increase the strength of the device and also for good looking. So the problem to us is, can we penetrate through the layer? Here is a glass to see the fingerprint. And the answer is yes. So here are the touch sensor results from our sensor. We compare the imaging without glass and the polymer film with 175 micron thickness, and also Gorilla Glass 4. This glass is used for the Apple device, and with two different thickness, 400 micron and 700 micron. And you can find that underneath, the imaging under the glass is a little bit degraded, with degraded resolution, and you see some interference and artifact. But most of the biometric content is preserved compared to the no glass imaging. These are some new results. We have our sensor, touch sensor, but the post-processing is by the commercial Verisonic system. So the sensor is ours, but the system is represent that maybe this is our next generation of the circuit and the processing unit. And we compare the fingerprint to optical sensor from the same finger. And from the optical and the touch sensor without glass, you can see the ridge and the valley pattern clearly, and also you see the poles, those white blight spot. And for under glass, you can see they're a little bit blurred because degraded resolution, but the ridge and the valley flow still match quite well to the other two. You can see some poles are still preserved here. And for fingerprint matching, we will take the features of the fingerprint. We call them minutiae, so it's include the bifurcation and the ridge ending. And you can find the minutiae appear at the same place in the three images. So next, I will introduce what the subcutaneous features we can use to get from our ultrasound fingerprint sensor. The first one is a bone contour. So bone contour has a low complexity, but also a low personal variance, means that your bone contour in the fingerprint may be very close to someone else or mine. So it's not a good candidate to do the matching or to do personal identity. And the other one is a vascular map. So it has a much higher complexity, but also high personal variance. So this is a good candidate. These two images are from this paper. They use the infrared sensor to get the fingertip vascular distribution. The image in the vascular distribution quite well matched to the real anatomy of the fingertip blood vessel distribution. However, this sensor is too big, so it's still not possible to integrate in a cell phone device at the current stage. So our idea is using the sensor 2D array and do a 2D ultrasound pulse echo imaging, so we can get a 3D Bolden imaging, and possibly can also do a 4D, 3D spatial plus time. We can get the Doppler signal, the blood flow, and the functional information. And we use this 3D and 4D information to recognize that you are you. So this will be some detail of how we do it. Take this for example. This is a 256 times 256 sensor, and we can take like 64 elements for the transmit aperture to transmit the focused beam, and we can scan along this direction. And in the other direction, we can do 64 element aperture to do receive beamforming. So by scanning this, we can get a 3D volume of the region underneath the sensor. So if we want to see a blood vessel here, we can do the transmit beam and the focus at the depth corresponding to where the blood vessel is. And we can do receive beamforming scanning all through this element, and with 64 element aperture, we can get a good quality imaging of the blood vessel. These are some preliminary results of the blood flow imaging, and this is our standard touch sensor, but it's interfaced by a commercial Siemens system. So this is someone's finger. You can see the bone contour is here and some speckles. It's about 8 to 9 millimeter underneath the surface. And we can see the blood Doppler signal, the blood vessel here. We can also do the spectrum Doppler. So this, like a live detect, it means there's a real person, and you've got the information from the pulse wave and your Doppler signal. So the idea will be like a two-step verification, and the device will store your fingerprint and also the subcutaneous information. So the first one, when the sensor get your fingerprint, it get to match the fingerprint to the store a fingerprint. If it got matched, you go to the next step. So we look for a certain location for the subcutaneous features. So if also the Doppler signal or the blood vessel distribution or even the pulse wave at the certain location match to the data stored on the device, the device recognizes that you are you, and you got it pass the validation, and you can use your device. Okay. So in conclusion, we already released our swipe sensor. There are two types. You can look at this. Just type ID key to search for it. Two types of swipe sensor are already released this April, and you can use this device for log into your Google account and to access your bank account. And the corresponding touch sensor is at its final testing stage, and we expect to be released by the end of this year or early next year. So for the next year, we will have the touch sensor ready and with the subcutaneous biometrics function. And with this, we have a more secure password to combine the surface fingerprint and the individual fingertip anatomy. And we will also investigate the possibility to do some diagnosis applications like the skin cancer detection and the blood vessel monitoring. So this is a guy a few weeks ago. He made a Soros hammer. So he used electromagnets and a fingerprint sensor to create a Soros hammer. So only the guy enrolled, get the fingerprint enrolled, can lift the hammer. So we are considering this maybe our next application. Thank you.